You know when you use an AI chatbot and the answer just appears? It feels like magic, right? Well, behind the curtain, there's this massive hidden engine working like crazy to make it all happen. Today, we're going to pull that curtain back and look at a huge optimization that has quietly made AI ridiculously faster and more efficient.
Okay, so let's get right into it. The single biggest problem in AI today isn't just about making the models smarter, it's the insane cost of actually running them. Sam Altman, the CEO of OpenAI, famously said the costs are eye-watering. And that's a huge deal, not just for the big guys, but for anyone, really, trying to build something cool with this tech.
So what is the culprit here? What part of this whole process is burning through all that money and all that computer power? If we can answer that, we can unlock faster, cheaper AI for everybody. And you know what? The answer is surprisingly simple, but it changes everything.
All right, first things first, the high cost of AI. To find our culprit, we gotta understand how a large language model, an LLM, actually comes up with an answer. Turns out, it's a step-by-step process.
When you type in a prompt, the model doesn't just spit out the whole answer in one go. Nope, it predicts the very first piece or token. Then it takes your prompt plus that first token and predicts the second one. And it just keeps doing that over and over until the answer is finished. This one-at-a-time process is key to how they work, and believe it or not, it's where the trouble starts.
Now, the GPUs that power these models are absolute workhorses. But to use them well, you can't just feed them one little request at a time. That'd be super inefficient. So you group a bunch of requests together into a batch. This is standard stuff, but for LLMs, it creates a huge bottleneck.
We're going to call this bottleneck the empty seats problem. And it's the perfect way to picture the incredible amount of waste that happens inside these super expensive AI systems.
The old school way of doing this is called static batching. Here's the deal. You get a bunch of prompts, bundle them up, and send them to the GPU. But here's the catch. The entire batch has to keep on running until the single longest response in that batch is totally done.
And this right here is where all the waste happens. Imagine you send in 4 requests. One is short, it's done in 2 steps. Another one's done in 3. But what if the longest request in that batch needs 8 steps? Well, the GPU slots for those finished requests just sit there, completely idle. They are empty, burning through electricity and money while they wait for the slowest one to finally catch up.
This brings us right back to our bus analogy. The GPU is the bus, and the requests are passengers. With static batching, the bus is forced to drive all the way to the end of its route, even if every single passenger got off at the second stop. All those empty seats? That's expensive hardware just sitting there, doing nothing.
Okay, so that's the problem. But thankfully, a bunch of really smart folks looked at this mess and said, hold on, there has to be a better way.
And that better way is called continuous batching. It was first introduced in a paper called Orca, and the idea is so simple, but it's a total game changer. Instead of waiting for the whole batch to finish, the second a single request is done, a new waiting request can jump in and take its place.
Let's go back to our bus. With continuous batching, the second a passenger hops off, boom, a new one who's been waiting at the next stop can get right on. The bus stays full, the engine keeps humming, and the whole system gets so much more efficient. No more empty seats.
Continuous batching was a huge leap, for sure. But then, an open-source library came along and took this whole idea to a completely different level with another brilliant idea.
That library is called vLLM. It came out of UC Berkeley, and honestly, it's pretty much become the gold standard for running AI efficiently. It uses continuous batching, yeah, but its real secret weapon is a technology called page detention.
So what is this secret sauce, page detention? Well, every time an AI is writing a response, it has to remember everything it already wrote. That's all stored in something called a KV cache, and it is huge. Page detention is just an incredibly smart way to manage all that memory. It's inspired by how our computers have handled memory for decades. Instead of grabbing one giant wasteful block of memory, it breaks it into these little pages that it can slot in anywhere only when it needs them.
And the difference here is just, wow. The old way, you had to block off this enormous chunk of memory just in case the AI wrote a really long response. Super wasteful. But with page detention, it only grabs these little pages of memory as it goes. The result? Memory waste drops to almost nothing.
We're talking under 4%. It's incredible.
Okay, so we fixed the empty bus seats, we've cleaned up the memory mess. What does this actually do in the real world? Well, the results are, frankly, stunning. Here it is. The headline number, 23x. That is not a 23% improvement. That is 23 times more throughput, more work done with the exact same hardware. It's just wild. To really see what this means, just look at this chart. A basic system is chugging along at maybe 81 tokens per second. An optimized system, like NVIDIA's faster transformer, gets you up to about 350. And hey, that's a great improvement. But then look at vLLM. It just blows them both away, hitting over 1,800 tokens per second. The leap is just absolutely massive.
And this isn't just some theory in a lab. Check this out. A report from Red Hat talked about a gaming company that switched to vLLM for their AI tools. The result? They cut their GPU usage and their server costs in half, 50%, and they did it without making anything slower for their users.
So, what's the bottom line here? It means AI gets faster, so apps feel more responsive. It gets way cheaper for companies to run. You can handle way more users with the same gear. But maybe the biggest thing, the most important thing, is that by smashing that cost barrier, it makes elite AI accessible to everyone. To small teams, to researchers, to startups, to people with big ideas but not so big budgets.
So this quiet, behind-the-scenes revolution happening inside the hardware is a total game changer. It means the incredible power of these huge AI models isn't just for a few giant labs anymore. It's out there in the hands of creators everywhere. Which leaves us with one big, really exciting question. Now that we have this, what are we all going to build with it?